Okay, so we're continuing on in section 6.4, arc length. And like I had mentioned, in our last class, we talked about how the arc length formula is derived. And then we looked at some examples of how we apply the arc length formula. And this particular problem, and incidentally, in those problems, we were able to find the exact arc length. Okay, and oftentimes finding the exact arc length requires some, well, it requires integration techniques. It requires, you know, sometimes some algebra is needed, you know, so that you can remove that square root. But here's an example, though, where we're going to need to estimate the distance, so, or arc length. So let me give you a moment to copy this example down. Okay, give you a few, maybe another moment or two. Okay, so in this problem, and maybe I'll use my stylus here. All right, let's get it here. One moment, class. Okay, so in this problem, we have a hawk. I'll have to use the mouse, it's better. A hawk flying at 15 meters per second at an altitude of 180 meters. It accidentally drops its prey. The parabolic trajectory of the following prey is described by this equation. Okay, and the trajectory, the prey, okay, falls until it hits the ground. And y is the height above the ground, and x is the horizontal distance traveled in meters. So what we want to do is we want to calculate the distance traveled by the prey from the time it has dropped until the time it reaches the ground, until the time it hits the ground. So what might be a good way to start this problem?
Draw a picture.
I agree. I agree with Maria. Draw a picture. And I'm sure Samuel agrees with that too. So let's draw a picture. And to that note, one moment here. Let me bring up the Desmos graphing calculator. There's also a calculator called GeoGebra as well that I'm looking into a little bit. But let's for now stick to the Desmos. And let me make this as part of the video. Let me get it here in my thing. Okay. Okay. So, all right. What we have to do is we type in the graph, which is hold on here, 180 minus x squared divided by no, I always do that. X squared divided by 180. Now wait a minute, hold on. Divided by 45, sorry. Okay, and I'm gonna hit that. And you know, it's supposed to draw a red graph, and I don't see any. I don't see a red graph. Why is that? I don't see this parabola being drawn in Desmos.
I just tried to
Scroll out.
and it didn't work for me either.
Well,
I think
it's
you should
actually,
zoom out.
we have to zoom out. So
Zoom out.
that's what, and I knew that. I was just testing you. So Maria and Renat are right. And so, well, let me ask you, what's the starting value of this parabola? When x equals 0, okay, when x equals 0, that's right at the moment when the hawk drops its prey. How high is that when x equals 0?
180.
180.
Well, yeah.
And look at the y-axis. That's only up to 6. So what we have to do here is in the Desmos, I'm going to go to where the wrench is here, graph settings, and the x-axis, well, I'll start it at 0 because the x is the horizontal distance, so it makes sense that, you know, at the beginning that's 0. And maybe I'll go up to like 100, okay? For the y-axis, I'll go from, say, 0 to maybe, well, I mean, I really don't need to have negative values, but I like to see my x-axis, so I'll use a y-axis starting at -10 and maybe go up to 200. Okay, and then I get a picture. Okay, so there is the trajectory. When the hawk drops its prey, there's the trajectory, that parabolic trajectory. Are there any questions so far? Okay, all right. Well, so now let's see. I'm just hitting, I'm gonna click on this little, in Desmos, I'm gonna click on the point here. Supposed to be able to click on the point, right? Let me see here. Well, I can see it starting at 180, but where does it hit the ground? How far, you know, what's the horizontal distance? I'll click right here. Looks to be 90, 0. Okay, so do you think that's going to be important? Let's see. And Renaud says if you click and drag on the graph, you can move around. And I just clicked on that the x-intercept, and so what are my limits going to be for this arc, this parabola? What are my x limits going to be? If I let x be my parameter, what would the x limits be? Would it be from, so we know 90 is important. That would be certainly your top limit. But what's your beginning limit, Samuel?
180 to 90.
Ah,
Or
so Samuel and Jacob, you say 0?
yes.
And that's correct.
Like when we're starting, the starting point would be 180 to 90. No.
Well, you're starting at x equals.
Oh, 0. Oh wait. Oh yeah, 0 to 90. Yes, 0 to 90.
All right. All right. So now what we need to do is formally use the arc length formula so we can get an expression for this arc length. Okay, that goes from 0 to 90. X goes from 0 to 90. Are there any questions before I move back to the the solution here? Okay. Okay. Well then let me go back to the. Hold on here. I got. Yeah, this is what I want. Okay. So. Well, now before we begin, what do you want to be the parameter? What variable would you like to be the parameter? So, I mean, Iker, what do you think? In other words, you have variables x, y. We could I was going to say x. Well, you see, look at this. Look at this. So y is a function of x. So in that case, it's easier to make x the parameter. So watch what we do here in the solution. I've drawn a picture. I've drawn a picture of the arc. Okay. This is the prey falling from 180 feet. Okay. Why doesn't, by the way, the prey fall just straight down? Why does the prey take a parabolic trajectory? Why does it take this arc here? Michelle?
Would it be air resistance acting on it?
Well,
It's falling.
it has to do, of course, the hawk
has
is,
velocity.
that's right. The hawk's flying horizontally. That's right, Maria. The hawk's flying horizontally, and so when it drops the prey is going downward, but it also has to be moving horizontally too. And now, Michelle, if we bring in wind resistance, that's going to be a whole nother issue. That's differential equations when we get into that a little bit. But we're keeping the model very simple, and I appreciate all responses. I'm going to let x just be x. That's going to be my parameter. Y will be 180 minus x squared over 45. And we know for the arc length, we need to take the derivative. If we're going to let x be the parameter, x is also a function, okay, of itself. So I take the derivative of x, okay, which is 1. Derivative of x with respect to x is 1. And the derivative of y with respect to x is negative 2x over 45. Okay, and then here's the arc length formula right here. Let me know if you have any questions up to here. So I mean, you're used to having, like in the denominator here, you're used to having dt, right? dx dt and dy dt. But that's when x is a function of t and y is a function of t, and t is your parameter. Here, x is a function of x equals x, and y is a function of x. So x is your parameter. And so you adapt the arc length formula accordingly. Okay. All right, let me give you a moment to catch up here. Please let me know if you have any questions. Okay, who's feeling, and I'll talk about how I got this approximation here, but who's feeling good down to the integral here, just before the approximation? Limits go from 0 to 90. Lepine's good. Okay. Baraka's good. Wonderful. Jacob's good. Okay. Tal's good. All right. Okay, Renaud, what I did was, hold on here. Little thing here. Let me just see here, one moment. Okay, so like if you had, say, x as a function of t and y as a different function of t, the arc length formula would be different. Okay, it would be, well, see, I'm a little short on room here, but let me just try to write the formula in that kind of you're used to, that you might be used to. So the arc length formula is the integral from a to b of the square root of dx dt squared plus dy dt squared. Hold on here. All right, dt. Okay, so this formula here is when x and y are functions of t, and t is your parameter. But in this case, you know, I have my arc here, and y is a function of x. So if I just let x itself be the parameter, then the arc length formula becomes this formula here. You see? Yeah, because instead of dx dt, where t is the parameter, I have dx dx, because x is the parameter. And then instead of dy dt, where t is the parameter, I have dy dx, because x is the parameter. Okay? Question, Iker? Okay, let me just see here. I didn't see anything chatted out here, but Renaud's comfortable. Okay, are there any other questions? Okay, well, we get down to here. Now, Here's the thing. This integral, actually, let me check one thing on this. So this particular integral, to be honest, does it look like it's something you could integrate using like a substitution? I mean, why are we taking this integral and saying find the decimal, calculate the distance? Well, and we're doing it with a decimal approximation. Could we do a substitution? I mean, if we were to use a substitution, the substitution, right, would be, well, u equals 1 plus 4x squared over 2025, and then du would equal 8x over 2025 dx, right? That would be, let me go to blue here. This would be like a substitution, but would it work? By letting u equals 1 plus 4x squared over 225, this becomes a u here, okay? But, and then du is 8x divided by 2025 dx. But are we going to be able to replace the dx using this substitution? Will it work, the substitution? That's right, Jacob. It will not work because you still have an x here. Hold on, I want that in red. You still have an x here, right? And you don't have an x here in your integrand. So this is not an easy integral to do. Okay, it's not necessarily an easy integral to do. You might be able to do it related to the arctangent somehow, but it's just not obvious. Maybe table of integrals would work. Maybe you could find something in the table of integrals, but it's not like in terms of the techniques you've learned, substitution, integration by parts, partial fractions, those kind of techniques. It's not obvious. So we're going to get the decimal approximation. The question is now, how do we get it? Well, so it used to be, of course, that we would require students to have a TI 83 or an 84, which could numerically integrate that. But over the years, more recently, maybe within the past 5 years, we realized that Desmos or GeoGebra can do integration numerically, and it saves students money because they don't have to buy the TI calculator, although they're really nice. But also, these Desmos or GeoGebra actually work pretty well. And if it saves students some money, we like that at the college. So let me go to Desmos here and show you how to do the numerical integration. Okay, I'm gonna go back in here to Desmos. One moment. Hold on here. I have to do the sharing here. Okay, hopefully this is the right one. Okay, so here I am, and what I'm going to do, can everybody see the Desmos okay? Is the window good? All right, Shiazi says yes. Good, good. So, and Samuel says yes. Thank you, Samuel. So what we do is, you see at the bottom left here, there's looks like a little keyboard. Okay, we click on the keyboard and it will show a keypad. And if you go to functions, if you click on functions, it brings up a lot of different functions. But if you go over to miscellaneous, MICS, okay, it has all these different kinds of features, and one of them is the integral. At the bottom left, there's an integral sign. Okay, and so Desmos can do integration, a definite integral. It can do a definite integral. So we click on, well, hold on, I'm in the wrong thing here. Hold on, let me get this off. Let me click on the second box and do this. I'll click on the integral, and you see I can put in my limits. Okay, my limits are 0 and 90. And then the integrand is the square root of, hold on here, it was the square root of 1 plus 4 times x squared divided by 2025. Now it isn't quite working yet. What do I need to put in? What's left to put in there?
Yeah.
dx.
dx. Okay, good. So we will put in dx, and then wow, look, it comes up right away. So 209.10527 is the answer, and so the arc length, which is the distance that this prey is dropped when the hawk drops the prey, the distance is 209.10527 meters. Okay, so and of course, certainly for the first exam, where you're proving you understand integration and the evaluation theorem, I of course didn't want you to have access to this numerical integration because you're trying to show me that you understand how to do it, the old-fashioned way, right? But certainly now for problems like these kind of problems where you need to use numerical integration, you would have access to some kind of integration calculator, like in Desmos here. Okay. There's also a GeoGebra. GeoGebra can do. How many have heard of this? Let me mention this. Are there any questions before I take this off the screen? Okay. Okay. So how many also have heard of GeoGebra? Okay, Jacob's heard of it. Okay, so that's something that I'm exploring too. In terms of I'm exploring that. I don't want you to, because you're in calculus too, and you're supposed to understand how to integrate things. Like if there's a situation where you have to compute an antiderivative, I don't want the computer. I don't want to have it where the Desmos or GeoGebra, the website you use, I don't want it to be able to compute indefinite integrals. Now, but definite integrals, like when you need to use them, when you need to use them for something like the example we just did, I'm okay with that. But the idea is that you show me that you understand and you learn, and you're gonna. So anyway, GeoGebra is another site that might be good for you to explore. It looks like it can do what Desmos can do, at least the basic things. Okay, great. Are there any questions on that? Okay, let me stop the recording.